I shouldn't have connected my audio to iPad, but I connected it somehow by my mistake. So my apologies. But I'll finish on time. So don't worry. Okay. Great. So as I promised on last Monday, I'm gonna go through the operations that preserve convexity again, and then we're gonna talk about optimization terminologies, and I'll show you some important examples just to kind of give you flavors of what on convex optimization is about. Okay. So last time we defined convex functions. So we say that a function is convex if it satisfies this inequality, which is quite important. But sometimes, in fact, in many times, we don't get to prove some function is convex using this inequality. It's often the case that you use some of these equivalent characterizations to prove that your function is convex. I guess the first one, we define this notion of epigraph. So we are so given a convex function or a function, we define some set, and the function convexity can be equivalently stated as set convexity using this notion of epigraph. Okay? And we talked about three characterizations. And the first one is basically if you have a convex function, then you so you pick a point and you draw a line or linear function that is tangent to your given function. If that gives you a lower bound, then your function is convex. Okay? And the second one is called the monotonicity of gradient mapping. So that is you basically look at this value. You change your vector from y to x, and you also look at the change in terms of the gradient, and they move in the same direction. In a sense that if you take their inner product, you get a non-negative value. Okay, and the last one is about second order characterization. So you say that your function is convex if the Hessian is positive semi-definite. And the example we saw was the quadratic function. So the coefficient matrix for the quadratic term Q. You know that the function is quadratic function is convex if that matrix Q is positive semi-definite. The thing I uploaded the lecture notes like a couple of minutes ago before this class. So if you are interested in going through the proof, you can refer to the note. Okay. I thought for the last few iterations, I thought it's important to prove the theorems, but I guess maybe it's important to some of you, but maybe not to others. So if you're interested, you can reach. But it's really important to remember the statements. Great. Okay. So I spent a few minutes last time on Monday going through the set operations and function operations that preserve convexity. But let's review this together again. Okay. So again, the idea behind it is that we have some simple structures of convex sets, and you can build more complex looking convex sets or functions by applying these operations. And conversely, when you have some complex looking function or a set, you want to determine whether it's convex or not, then you can basically apply these operations to decompose the big picture into some pieces, and you analyze each piece. And if you prove that each piece is a convex set or a convex function, then the original big thing is also convex. That's the idea. So intersection. So let's say some intersection of I, which belongs to some set I, Si, some Ci is convex for any convex sets for any family of convex sets. So here the set I, the capital I, doesn't have to be finite. It doesn't have to be countable. Can be like continuously infinite. Can be there can be like as like infinitely many sets in the family. And the scaling. So let's see, is a convex set, and alpha is some in any scalar. In alpha times c is called a scaling of the set, and this collects the vectors. So for any vector in the original set C, you take the scaling of that vector. That's it's kind of intuitively clear, right? You are just changing the magnitude of each vector, and then you preserve convexity. And Minkowski sum. So let's say C1, C2 are convex sets. So last time I took some like K convex sets, but you can recursively apply this operation. So let me just take two sets, and alpha 1 and alpha 2 are any scalars. They don't have to be negative. Now I take alpha 1 C1 plus alpha 2 C2. Okay. This is defined as so you take x1 from C1 and x2 from C2, and what you collect is alpha 1 x1 plus alpha 2 x2. This is the Minkowski sum. If you are interested in like linear programming or polyhedral theory, there's the notion of Minkowski Weyl theorem. So this basically, so if you look at the feasible region of a linear program, it can be decomposed into a cone and a polytope. Okay, so this means that what this says is polyhedron is equal to cone plus a polytope. And here, this is the Minkowski sum. Okay. What it says is like you have a polyhedron that can be unbounded, but you can always separate the bounded parts from the infinite directions. And here the notion right here is the Minkowski sum. I'm just this is not completely related, but again as a side remark. Product. So C1, C2 are convex sets, and this is the product of these two sets is denoted as C1 times C2. And again, you are taking one vector from the first set and another vector from the second set. But here you are taking the the vector obtained by appending these two. You are building a high dimensional space, high dimensional set. Now the next one, so let's say I have an affine mapping let fx is given by ax plus b. So this is like you're taking a d-dimensional vector, and then you are sending this to the p-dimensional space. So the matrix A is a p by d matrix, and B is a p-dimensional vector. Okay. What you do is f of c is for any vector in the set C, you are taking ax plus b. So again, the affine mapping is close to linear transformation. Well, it's a linear transformation, and you are adding this bias term. And so this is just something that's linear. And this linear mapping always preserves the original structure. That's what you can remember. And the affine inverse image is the following. So we use the same affine mapping. What we do is we take a vector x whose affine mapping, okay, belongs to the set C. So ax plus b belongs to set C. So this is the inverse procedure. And proving whether this operation's convexity is not difficult, just because I guess you can I recommend you go through the definition and just to and see whether this actually preserves convexity. And things are easy because this thing is linear. Okay. So great. Now we talk about function operations. So here let me take two functions, f1 and f2. Okay. But here we need to be careful about taking non-negative weights, because if you remember the definition of concavity, so if you take negative scaling of a convex function, you get a concave function. So multiplying a function by a negative number doesn't preserve convexity. So we need to take non-negative numbers. So alpha 1, alpha 2 are non-negative scalar. Then having alpha 1 f1 plus alpha 2 f2 is convex. Let me give you, so for the second operation, let me give you one example. So this thing is a linear function in R2, or for the univariate case, we get a line segment in R2. This is a linear function. Let me also take another linear function. That is this. Okay. Let me take one more. Something like this. So we have three linear functions. And we know that our linear function is convex. Okay. So all of these three functions are convex. So what I do is to take the maximum of these three. So again, this is my domain, x. And the y-axis represents the function value. Okay. So for each x, let me define another function that is defined as the maximum of these three values. So if you do that, you get is this thing. Okay. And in fact, if you take finitely many linear functions, the maximum of that finite collection of linear functions is called piecewise right? piecewise linear function. And if you look at this thing, this piecewise linear function is convex. It resembles the quadratic function or parabola. Okay. But in fact, there can be non-convex piecewise linear functions, so you have to specify that this is a convex piecewise linear function. For example, this thing is an example of non-convex piecewise function. But if you take maximum of linear functions, you always get a convex piecewise linear function. So in general, maximum of any collection of convex functions gives you a convex law. And here we took finitely many convex functions, but you can take infinitely many convex functions. But taking the maximum still preserves convexity. The proof is this proof hint, proof idea. Use epigraphs. And we learned that any arbitrary intersection of convex sets gives you a convex set. So what you need to prove is that the epigraph of this maximum is intersection of epigraphs of individual things. Then you can argue this. Right. I guess next thing is kind of interesting. So here we have a function, let's say gxy is convex in x. So what it means is, okay, so I have two parts, x and y variables, and I say that it's convex in x. What it means is that for any fixed y, gxy is convex. So if you fix the y part, then the function depends only on the x part. So it becomes a function in terms of x, and that's always a convex function in terms of the x variable or any fixed y. And also, gxy is convex in y. So these are my two conditions. Again, for any fixed x, now the function becomes depends on y only, and that function in y is a convex function in terms of the y variable. Okay. It's quite interesting that even if this function is convex on one part and the other part, it doesn't guarantee that the function is convex in if you take the whole vector x and y. Now the operation here as follows. So now let me define my function f of x as follows. What I do is I take minimum of gxy. So now I take, so for any fixed x, okay, what I do is I take the minimum value of gx comma y, where y can be anything from some convex set C. From the assumption, if you fix any y part, we have a convex function. But at the same time, moreover, we are collecting, the all possible choices for y, and I take the minimum value among them, then that's still convex. It's non-trivial to prove, but it's okay just to remember the statement. Okay. And perspective function is defined as follows. So you have, let's say, g x is convex. Now, I'm augmenting the function by adding one more variable. Okay. And the perspective function is defined as f x comma t. And this is defined as t times g of x over t for t positive. There are some application. I think it was some type of portfolio optimization problem, and it's easier to use this transformation. So you start with some convex function, and then you are building a function in a higher dimensional space, and this is sometimes easier to work with, depending on your application scenarios. Right. And a fine composition. So again, this is so f, let's say y is convex. So this r p to r. Now g of x is ax plus b, where a is a p by d matrix, or a d by p matrix. No, a p by d matrix, and b is a p-dimensional vector. Now what I do is f of gx, or f of ax plus b, is a convex function. So you are taking a linear affine mapping first, and then apply the function, you get a convex. And in general, if you have two convex functions, f and g, this is convex, and you still get a convex function. Uh, no, I didn't. Any question? Okay, then let me give you 3 minutes to argue that these two functions are convex. So these are related to something called the facility locations. These are two types of distance functions, and I want you to argue that these are actually convex. Okay. So x minus y. This is unknown, and we know that this is uh x for any fixed y. Now, if you look at this function, this is basically the maximum of some convex functions. This is always convex. And the second example, well, I guess this is maximum, so this is quite clear. But even the minimum gives you a convex function. That's kind of not straightforward. But the reason is that, and we know that this is also convex for any fixed x. So if you view this x minus 1 norm, or x minus y norm, if you view this as a function in terms of x and y, then this one, if you take convex as C, this is obtained from minimizing out variable y. Okay. So this is, we applied this operation. That's why we're getting a convex function. But the restriction is that for the first case, we can take any set C. But for the second example, we need to take a convex set C to get a convex function. Any question? So we just completed talking about convex sets and convex functions, and let's get to the order of optimization. So an optimization problem has the following form. So we have a function f that c, and we typically write a problem as this one. And here x is called the decision vector, or you could call them as decision variables. And if you have a like financial portfolio problem, which is like we're gonna talk about it in a minute. So X can capture like how much portion of your budget can be allocated to certain financial product. That can be example. And also, if you think about facility location problem, I guess you are a mayor of a city and you want to decide the locations of fire stations to build. That you can use a variable to capture such decision. And here, this function f is called the objective function. So this is the objective that we need to achieve or optimize. We are throughout this course, we'll typically stick to minimization problem. This function f typically captures the cost function. Sometimes you want to maximize your profit, then you need to write down maximize here. And to have some tractable algorithm, if you have a maximization problem, the objective has to be concave. Okay? In that sense, linear functions are good because you don't have to worry about minimization or maximization because linear function is both convex and concave. But if you have a nonlinear function, you need to be careful about minimization and maximization. And here, this set C has different names. Some people call it a domain, or a feasible region, or a constraint set. I guess I'll use some of these names time to time. But they mean the same thing. So what it is you are basically taking vector x from the set C that has the minimum value of the function. That's the meaning of the optimization problem. I guess when you deal with like some like machine learning problems, I guess like many problems are unconstrained, which means that the set C can be the entire Euclidean space. You don't put any restrictions on your decisions. But if you're coming from like industrial engineering, where you gotta solve some operations problem, then there typically exists like many restrictions and constraints. Like you have a budget constraint, like you have to choose money out of your pocket. So your budget is not limited, not like unlimited. And also like some production lines have certain capacities, cannot operate like millions of machines at the same time. There's a restriction on how many machines that you can operate simultaneously and so forth. Yeah, so such thing can appear. If you are coming from like the control side, like which is quite common in mechanical engineering, electrical engineering, you typically have certain constraints and restrictions that are written in terms of like affine equations and so forth. And the set C can capture those constraints. Okay, the next set of terminologies. So any vector that belongs to the domain is called a feasible solution. It says just remember this this terminology feasible. It satisfies the constraint. And we say that the problem is feasible, not just a single vector, if it has a feasible solution, which means that the set C, the domain, is non-empty. There's a vector that satisfies all the constraints. If there's no such a vector, then we call the problem infeasible. Okay? Which means that there's no feasible solution. Okay. We are trying to minimize the function value, but you might realize that, well, I guess if you don't have any, well, depending on your set C, you might be able to decrease the value as much as you want, which means that the value can go to minus infinity. Then you say that the problem is unbounded. Okay? I guess in many practical scenarios, you don't get to observe unbounded problem, but you can theoretically build unbounded optimization problem. Okay. When you know that there's a certainly the minimum value is greater than certain thing, like maybe like you want to decrease the cost, and you know that the total cost has to be something positive, right? The cost cannot go to minus infinity. In that case, your problem is called bounded. Okay? There's a lower bound on the minimum value of your objective function over the set C. Let's look at this example and determine whether it's feasible, unbounded, or bounded, or infeasible. Well, I guess let me give you an answer. It's not that too important. Well, so this is the circle around the sphere around the origin with radius 1. and this thing defines a hyperplane or Hopf space. Okay, if you take the intersection of these two, you get an empty set. So if you have a domain being C, then the problem is infeasible. Okay? There's no solution satisfying these two constraints. This is infeasible. And what about this? The problem is feasible, right? Because the domain is non-empty. And, we know that the quadratic function, the coefficient is positive, and this is at least 0. So the problem is bounded as well. Feasible and bounded. The last set of terminologies. So the value of this problem, which is the minimum value of the objective function over the solutions from the domain C, is called the optimal value. Okay. And if the problem is infeasible, right? Okay, let's talk about okay. Right. So if the problem is infeasible, which means that there's no solution even satisfying this constraint, the set C is empty. And now you are trying to minimize the value. So then because there's no solution satisfying the constraint, we set the value of x, the value of this optimum value to plus infinity. There's nothing that's practically achieving for the objective function. And if the problem is feasible but unbounded, again, that means that you can decrease the function value as much as possible. So in that case, you're setting the value as minus infinity. And if the problem is feasible and bounded, then the optimum value has to be finite. And any solution whose objective value is equal to the optimal value is called an optimal solution. And you say that the problem is solvable if there's an optimal solution. And if not, the problem is unsolvable. And you might ask, why do we even care about these things? Well, let's look at this example. And let me give you 1 minute to decide whether the problem is solvable or not. Okay. Again, the problem is feasible because the set C is not empty, and this is bounded. Again, the quadratic function is always a negative. But is it solvable or not? Well, you draw this picture. This is a quadratic function, parabola, where the minimum point is x equals 2. And what I take as the set C is open at x equals 3. But so this is my feasible region, and you care about this part of your quadratic function. And this point x equals 3 seems to give you the optimal value. Well, that is actually the optimal value. So OPT is 1 when x equals 3. But this is the feasible region is open at x equals 3. So you don't get an optimal solution. The problem is unsolvable. So this is on, well, I guess this is an artificial example, but I guess it's good to differentiate like what it means, these terminologies with this one. Okay. Any question? Yeah, when you talk about minimization problem, then I guess the optimum value will be the infimum. That's lower bound, or yeah, whatever you call it. I guess if you're familiar with like mathematical analysis, there's this notion of open sets and closed sets, and whether primum exists or infimum exists, and this kind of notion appears here. I guess when you deal with some like linear programs or some like relatively simple problems, you don't get this kind of issue. But when you start dealing with like complex nonlinear functions like logarithms or negative entropy, you have to be careful about positive numbers. And when your variable goes to 0 or goes to 1, and you might get into trouble. And this kind of issue about whether your domain being open or not can create some problem. And in practice, you are adding some like small number when your variable tends to kind of reach the boundary, and this thing can happen in depending on your applications. Okay. So we just talked about optimization basics, and then what is a convex optimization problem? Well, we dealt with we defined convex functions and convex sets, and if you have a convex function as the objective and convex set for the feasible region, then you have a convex optimization problem. Okay, and you take convex function and you have to minimize it. If you have a convex function but its maximization problem, then that is not a convex optimization problem. Okay. Great. So here we have this constraint that x has to come from the set C, and it can be rewritten as ICX equals 0 or less than or equal to 0. Remember that the IC, this is the indicator function. It has value 0 if the point belongs to the set C. It has plus infinity if it does not. And here we well, one question is that why not we set this function to equal to 0, not using inequality. Okay. It's a common practice to use inequality when you have a convex function on the left. Okay. Well, I guess for the indicator function, there's no difference using inequality from equality. But for general convex functions, using inequality and using equality are different. Okay? You could create a non-convex set if you use equality. I'll get to that later soon. But again, when you have a convex function, you have to say set inequality. That's important. And well, for our problem of this indicator function, it can also be equivalent to f of x plus IC of x. Why is this original problem equal to the third one? Well, whenever x is outside the set C, you have the plus infinity. And your objective is to minimize the function. But every time you get a plus infinity value, such a point doesn't have any meaning. So you have to consider the set of points where this part becomes 0. And that's equivalent to, considering, the point in the set C. Great. Here. So, this is any problem that has this form is called a convex programming problem. So, in general, we consider a convex optimization problem. But when you have certain like specific explicit functions, like quadratic functions or linear functions or negative entropy, and you can express your constraint set using those functions and write down inequalities and equalities like this, then you call the problem a convex programming problem. If you are familiar with linear programming problems, it's an extension of linear programming. For linear programming, we take linear functions for f, g, and h. Okay? But the convex programming is basically the same, but f and g can be any convex function. Okay? But here we have equality constraints. Okay, you cannot put on nonlinear convex function for h here. Okay, when you want to set some equality constraints, this hi here has to be a affine function or a linear function. Okay. So again, so when f is convex and the inequality functions g's are convex and the equality functions h's are affine or linear, then this problem is convex. And you can so you can prove that the set of solutions satisfying all these constraints is actually convex. But you can also find an example where if you change some equality by inequality, then you get a non-convex set. Okay? When you have I guess like no, when you have not inequality. So when you have a nonlinear convex function for h, but you still have an equality constraint for that function, then the resulting set is not convex. And situation. Well, let me actually give you an example. Think about x in R2 and XL2 norm. So we know that any norm is a convex function. And let me add the equality constraint like this. Well, I guess if you are not happy about having non-zero value on the right-hand side, let me move the right-hand side to the left-hand side and have -1 here. Still, the norm subtracted by 1 remains convex. And if you look at the set of this set, this is in fact the sphere, but this middle region is not part of the set. So if you look at the sphere, but if you have all the points inside this wall, then you get a convex set. But if you have the equality here, then you're missing out this point inside. So you get a non-convex set. Okay. But in fact, let me give you one more thing that might be interesting to some of you. Well, this is a special type of non-convex constraint. And you can actually optimize a convex function for this non-convex set. And the required method is called Riemannian optimization. So for the last few years, there has been a large amount of activities about extending, gradient descent and all these convex algorithms to this kind of set of Riemannian manifolds, and we gotta you can deal with this kind of. But in general, if you have a more complex looking constraint, then we cannot. There's no way of dealing with it. Anyways, okay, let's move on. Today I'll talk about a couple of examples, and in the next class, I'll talk about the others. So the first one is called portfolio optimization, and I guess I'll explain the problem in the context of financial planning. So let's say I have the different financial products, like including stocks, bonds, and bank account, anything. And here, my problem, what I want to solve is this allocation problem of my budget. Okay? I have my budget, and my entire budget is 1, because I'm talking about proportions and fractions. And I want to determine, okay. So each xi, means the fraction of my budget allocated or invested to this financial product I. Okay? And in fact, it can be a negative number if you take a short position. Okay, and if it's non-negative, it's a kind of the usual thing, the procedure of long position, and you can combine these things. Okay. And if you take the summation of their absolute values, and it's the total leverage value. If it's greater than 1, it means that you actually incurred a large amount of leverage. Okay. Now, P subscript I is the initial price of your asset class I, and PI prime is the final price. And my return value is measured by the fraction of increase for that asset class. Okay? So this is the change divided by the initial price. And here Ri is a random variable. But so if you invested, so here X here, determines your allocation strategy, and the final return will be given by R transpose X, which is the summation of Ri, the return times the proportion of your investment to that item I. Okay. Here R is a random variable with mean mu and covariance matrix sigma. Okay. And the expected return by the linearity of expectation we get mu transpose x, because mu I is expected value of Ri. And if you take the variance of R transpose X, then you get this value, X transpose sigma X, because R has the covariance matrix sigma. Let me skip this part. So if you are familiar with financial planning, I guess here the expected value of your return measures your profit or revenue. And here we also need to care about the variance term, and we don't prefer portfolio that has a high variance value. It means that there's some kind of there can be a big amount of fluctuations in your return values, and you don't want that. And here, so this variance term measures the risk of your portfolio. So you want to basically increase the expected return while minimizing the risk value. And that can be captured by solving this problem. Okay. Let's look at the constraints first. So 1 transpose X equals 1. This means that your X captures your allocation strategy. Okay. And let's look at the objective. Well, I want to maximize something. So forget about the second term. So the mu transpose X is the expected return. So I want to maximize the expected return. But I have this minus gamma. So gamma is a positive number. This gamma is some parameter you can choose. To maximize this objective, I want to increase the value of this linear term, while I want to decrease, this quadratic term. Okay, so you want to, and then here X transpose mu sigma X captures the variance. This is a variance, so this captures the risk term. So if you look at this combination of linear term and the quadratic term, then you might be able to, achieve this goal of maximizing the return while minimizing the risk. And depending on how you are willing to take the risk, you can choose a different value for gamma. If gamma is chosen to 0, then you are completely agnostic to the risk, and you are just kind of you might be managing a hedge fund. If you set a very large value to the gamma, then your sole objective is to control the risk while compensating while sacrificing the return value. And also you don't want to borrow money from the bank, then you need to take long positions only. You want your variables are restricted to be non-negative. And sometimes you might allow leverage, but you don't want to kind of take high risk. So you might want to control the total leverage value by some proportion capital B. Okay. Now the question is this a convex optimization problem? Well, first, I guess the constraint sets look okay. The first one is a hyperplane. We know that hyperplane is a convex set, and C prime look like some convex sets. And then putting these two constraints at the same time doesn't matter, because any intersection of convex sets gives you a convex set. But what I'm concerned about the objective, first, this is a maximization problem. Okay. Well, so to do this, well, it's actually known that just believe me for this. If you take any covariance matrix, it's always positive semi-definite matrix. So sigma here is positive semi-definite. Okay. But if you look at the objective, this is a quadratic function, right? But quadratic function. But if you look at the quadratic term, okay, if you take its Hessian, what you get is minus gamma times sigma times 2 or something. what's important is that you have a negative scaling of a positive semi-definite matrix. So it becomes a negative semi-definite matrix. This is not a convex function. So let me write it down. So this is f of x. Hessian of f is minus 2 gamma sigma, and this is negative semi-definite. Well, in fact, minus f of x is minus mu transpose x plus gamma x transpose sigma x. Now, if you look at this function, and now you take the Hessian of the second function, then you get a positive semi-definite matrix. Okay. So what it means is that minus f is convex. Okay. So the original function f before taking the negative sign was concave. Okay. So you were maximizing a concave function. Well, that's actually a convex optimization problem by this following relationship. So the left-hand side is the original maximization problem. Okay. And you can rewrite the problem in the following way. So I have -1. Okay. When you have -1 in front of the maximization, you have to change the, this mean. Max from max, you have to change it to minimization problem. And then you have to multiply -1 for the objective as well. Okay. In general, max of f of x and x belongs to some set C. This is equal to minus mean minus f of x, but you have the same constraints. Okay. So what this says is that concave maximization is equivalent to convex minimization. I have 2 minutes, but let me quickly go through the second example because it's related to portfolio optimization. My apologies. But I will, review this. I'll get back to this example one more time in the next class. So there's another important area called uncertainty quantification. This is related to statistics. So the problem is the following. So we have a portfolio X, and we have the covariance matrix. Then the risk is measured by this quadratic term X transpose sigma X. Okay. But this is some random value that we don't really understand. If you understand the financial market with a complete knowledge, then I guess you can get a high profit. But that's not the case in practice. So which means that we don't have access to the exact value for this matrix sigma. But there's a way of estimating or getting an approximate value of sigma based on the historical data. So let's say we have on some estimation sigma bar, which we believe is kind of close to the actual value sigma. Okay, but there can be some errors depending on your data. So instead of the actual risk term, we have a quadratic function with this approximate covariance matrix sigma. And it could, give you a good approximation, but sometimes it results in a high error. Now my question is, I don't want to have, errors in my financial planning. Then can I kind of be a little bit more, cautious about, using this value sigma bar? And that is the idea behind uncertainty quantification. So the idea is that, well, I guess sigma bar, I know that it's kind of close to sigma. And using this information, can I build a portfolio that's kind of safe to the worst case scenario? Maybe like sigma bar is kind of far from sigma, but even in the worst case, can I guarantee that my portfolio is good enough? That's my idea behind it. Well, the estimation noise, I mean, this is coming from statistics. You can even prove that, if you have enough data, the estimation errors can be bounded. So what it means is I can set off some number epsilon here if you have a large data set. Okay. That part is okay. Well, okay, again, this is the unknown covariance matrix, and this is my estimated covariance matrix. And you can measure the noise or error in terms of the number of data points. So in theory, if the number of data points is infinite, then you can set a 0 value to epsilon. But so let's assume epsilon is given here. Then my next question is, can I build a kind of safe portfolio? Well, so I'm gonna get back to this later. But so what I saw is instead of this single sigma bar here, I kind of consider possible perturbations around, this sigma bar. So I'm capturing the estimation noise by adding one more set of variable s here. Okay, so this is if you solve this problem, this computes the worst case possible scenario of perturbing your, estimated covariance matrix. And if you look into that, that gives you, the worst case risk of your given portfolio. That's how you kind of control. So you choose certain portfolio, and then you have your estimated covariance matrix. Now you solve this problem, then this gives you the worst case possible risk. Okay, and by that information, you can, I guess, try to change a different, try to come up with a different portfolio and stuff. I'll get back to this later. Have a great vacation. And I'll see you later.
왜 필요해요? 여섯 명이네. 이건 한 번에 경험 사람이 그냥